Hello, everyone. Mr. Minnick's my name. Math is my game. You're joined um, this is 7:50 a.m. Mr. Minnick on payday Friday, and he is joined by his first period class. We're all smiles today. First period. It's the weekend. It's payday. It's Friday. Well, you guys don't get paid today. Well, maybe anybody get paid today? Working? Nobody? Sorry. Okay. I'm excited about this lesson. It's chapter 2, section 6. It's families of functions is the title of it. The objective, the goal by the end of this lesson, which I mentioned that this material is going to be used all throughout the year because we're going to be graphing functions all year long. But you should be able to identify, you should be able to describe, and you should be able to compare the three types of transformations of functions and relations. In 2.1, we talked about relations, how they're a set of ordered pairs, and how sometimes relations are functions and how sometimes they're not. So some of that material is probably going to come back up also. So 2.6, families of functions. How's everybody doing so far? Good? All right. So I always use the Sheen family when I talk about this stuff. Anybody know the Sheen family? Charlie Sheen, 2.5 Men. Know who I'm talking about? So let's go to Goggle Images and let's take a good look at Charlie Sheen. Not too good of a look, though. Got to be careful what you Google search nowadays. Wild Thing. Boy, the Indians are doing real good now, aren't they? Anybody ever see that movie with Wild Thing, Rick Vaughn? Remember that one, the baseball movie, Hot Shots? Good movie. If you get a chance, check it out. So here's Charlie Sheen. That's a good picture of him. We'll send this to a new page. Welcome to the new page, to the new page. All right, so there's Charlie Sheen. Good-looking guy. 2.5 Men. Now, Charlie Sheen's dad is, anybody know Charlie Sheen's dad's name? Is Martin Sheen. Martin Sheen. Martin Sheen played the President of the United States a while back on a show. See if I could find a good picture of Martin Sheen where he's facing the same way that Charlie Sheen was. I don't know. Maybe that's not the best one, but we'll go with that one. We'll send that to the same page. All right, so there's Martin Sheen. Well, we got to find one more here. One more here. Does anybody know Charlie Sheen's brother? What is it? It's Emilio Estevez. Emilio Estevez. Emilio Estevez. I don't like the mustache ones. Those kind of creep me out. Speaking of mustaches, has anybody ever noticed that all men from Pennsylvania have mustaches? All men from Pennsylvania. This is a younger picture of them, but I'm going to go ahead and take that one. Maybe I should have tried to get them all from the same age to be fair, but all right. I am going somewhere with this, so just be patient with me. All right. So Martin Sheen is the dad, Charlie Sheen, and Emilio Estevez are the offspring. You picking up what I'm putting down? So what can you say about father to son to son? What can you say? Do they look the same? Kind of, a little bit, somewhat. I'd be really curious to see where Martin Sheen lives. I think he lives somewhere out west, like in Wyoming or one of the Dakotas or something like that. Probably on a ranch somewhere. And Charlie Sheen, if I had to guess, I'm sure he probably lives in L.A. And Emilio Estevez, last time I heard, I thought he lived like in Phoenix or something like that. So they live in different places, but they kind of look the same. They're of the same bloodline, and so is it fair to say that they share traits that are common to all of them? Okay. So what we're going to do is we're just going to start off with a relation, with a function, and we'll kind of, I had this lesson in my advanced class the other day ago, and we'll kind of work in a different way than we did in there. So suppose this relation passes through the point, the origin, and then 1, 3, the point 1, 3, and then we'll go to the point, the next point next to that will be 2, 4. Well, it's going to be a fun day today. So there's 1, 3, 1, 3, 2, 4, 2, 4, and I want one more point on this relation, and I'll make that 5, 1. Make that 5, 1. So this is going to be a weird looking relation. Okay, it's going to go like this. Whoop, whoop, whoop. You like the sound effects? That's it. That's the relation. Okay, so what we'll say now, is that a function? Yeah, it passes a vertical line test, doesn't it? For each input, there's one output. So let's say the given relation is a function. The given relation is a function. So we'll call it f of x. We'll call it f of x. Okay? We'll call it f of x. It is a function, f of x. Now what I'd like to do is I'd like to take that function, and I don't know if anybody noticed about Martin Sheen and Charlie Sheen. You probably can't tell from these pictures, but Charlie Sheen, how tall would you guess that he is based on what you've seen on him in 2.5 Men? Pretty tall? Maybe like 6'1", 6'2". I don't know if you know this, but Martin Sheen is a wee little man. Martin Sheen's maybe like 5'6", 5'7", and Emilio Estevez is about the same height as Martin Sheen. So it is possible that we can take something like this relation here, and it is possible that we can make that thing taller. Now, that's going to be kind of difficult to do. I'm not going to be able to stretch it out like that. But suppose we had something that still passed through the origin, but instead of going through 1, 3, suppose this thing went through 1, 6. Instead of going through 2, 4, suppose this thing went through the point 2, 8. And instead of going through 5, 1, suppose this thing went through 5, 2. So it would look like this. Whoop, whoop, whoop. Now, how does the green one compare to the red one? What do you think? What thoughts come to mind? How do they compare? Yeah. They kind of look the same, but it's bigger, right? It's how else could we describe it? Similar. So when we talk about similar figures in geometry, similar figures have the same angles, and the side lengths are proportionately bigger. So I don't know if I'd go so far as to say they're similar because the angles kind of are a little bit different, but they kind of look similar. We couldn't call them similar figures, but what else could we say? There's a T word that should come to mind. Bueller. Tangent? Well, they have a common vertex, but I'm looking for something that it seems pretty obvious to me. Maybe it's just me. I don't know. Triangular? It is kind of triangular, but I'm trying to describe how the green one compares to the red one. Maybe there's an H word that comes to mind. It is well, it's not a translation, but I'm glad that you're thinking of that because that's one of the 3 types of transformations. How does the green one compare to the red one? Huh? Dilation. Somebody in my advanced class the other day used that word. I'm not going to use that language. I'm going to have to look that up to know what that means. Dilation is when it goes, what, smaller or bigger or something like that? Or both? Okay. So, kind of, yeah. If you're used to that dilation, I'm going to look that up and I'll get back to you. That's a good answer. But there's a T word I'm thinking of. Somebody who's 5'6" compared to somebody who's 6'2". How do they compare? They're taller, right? Does that make sense? Does that make sense? Okay. So the deal is, what I want you to realize is that if we were to make a table here, if we were to make a table, we have certain x values, and we also have certain y values, right? You with me? Now, rather than writing y, and this is a big thing here, rather than writing y, I'm not going to write y, because my y values come from the function. Right there, I'm going to write f of x. You see what I got going on there? Okay. So my x values are 0, and 1, and 2, and 5. And my f of x values that correspond are 0, and 3, and 4, and 1. Does everybody see what I got going on there? I just made a table of values for the red function. Now what I'm about to do is to go ahead and make another column. And here I'm going to put the y values of my green function. The y values of my green function. Okay. So what are the corresponding y values of my green function going to be? Anybody? 0, 6, 8, and 2. So if I wanted to know how these compare, how do they compare? 0 and 0 are the same, but how does 3 compare to 6? How does 4 compare to 8? How does 1 compare to 2? Yeah. It's times 2. It's twice as big. The y values are all twice as big. Does that make sense so far? Good. So what I like to say about that, and maybe we'll do one more on this graph, and then we'll try something else. So I want to do one more on this graph. I want to go one more time. 0, 0. What if I had this point here of 1 comma 1.5, and then 2, 2, 2, and then 5 comma 1/2. So whoop, whoop, whoop. So let's add one more column to this table. And so what are our f of x values here going to be? Anybody? 0, 1.5, 2, and 1/2. Okay, so if we compared the original function to this one, how do those compare? It's divided by 2, or it's half the size, or it's just shorter, or not as tall, right? So what we see here, somebody mentioned the word dilation. I'm not familiar with that language, and that's not the language that's used in the Algebra 2 context. But you're probably onto something. I'll bet that's pretty accurate. But the language that we use is the first type of transformation that we're going to talk about. So we're going to say for any function f of x, k times f of x, k times f of x is a vertical stretch or a vertical, the opposite of stretching something out is kind of squishing it down. Anybody know the fancy word that we're looking for here? Bicyclists who wear those tight shorts know about them? Compression, yeah, or vertical compression. Okay, vertical compression. So that's the language that we use here in Algebra 2 when we're talking about a function getting taller or getting shorter. A vertical stretch or a vertical compression. So the whole dilation thing, I don't know what class you talked about that in, but in this class we're going to use vertical stretches and vertical compressions. Okay. So I think I can make this split screen. So when we had that vertical stretch, like we did from the red one to the green one, we multiplied by 2, right? So how are we going to stretch a function out? What would we have to multiply a function by to make it bigger than it already is, do you suppose? What kind of number would we have to multiply it by? Bigger than 1. Awesome. Nice job. Bigger than 1. So anytime we have a vertical stretch, the vertical stretch happens when our k value is bigger than 1. And so how do we vertically compress something? This one's a little trickier. It requires thinking inside the box, kind of, so to speak. To compress something, what kind of number are we going to have to multiply it by? So, I'm hearing a couple different things. I'm hearing less than 0. I'm hearing a half. A half is a certain type of number and it lives in a certain space. What are we thinking? That's perfect. Greater than 0 and less than 1 is perfect. Yeah. The k value's got to be greater than 0 but less than 1. Remember the between this notation we used last week? There it is. So if we multiply the function by some k value, k is constant, by the way, in case you didn't know. So for any function, f of x, k times f of x results in either a vertical stretch or a vertical compression. Now somebody mentioned something about something being negative earlier. To kind of to not have to worry about that, I'm going to go ahead and put these k's in absolute value symbols. Okay, I'm going to put them in absolute value bars. The reason I'm doing that is because sometimes we're going to multiply a function by something negative, and that's going to do something entirely different. So if you're keeping track of the 3 types of transformations, here's the first type of transformation: vertical stretches and compressions. That's the first type, the first of 3 types of transformations. Doing all right so far? All right. Well, it's Friday. They're going to be telling jokes today. I really wish I had some good jokes, but I can't think of any more. At least not that are school appropriate. And I've got that tooth. I've got that achy. I got that tooth that's been bothering me. Did I tell you about that? Yeah, they. I tried to get a dentist appointment, but the only time they could schedule me for was 2:30. So, we're going to be looking at some parent functions. Here's the first parent function I'm going to show you. It's the parent linear function. The parent linear function. We're going to look at least 3, maybe 4 today. The parent linear function is y equals f of x equals x. That's it. This is the parent linear function. Okay. This is the parent linear function. So what I'd like to do is I'd like to go ahead and graph it, and then we'll try to come back to it and see if we can tie in all these transformations to it. So the parent linear function, table of values, x and f of x. Now the f of x is actually equal to x. This is a unique function. Anybody remember what it looks like? Think about your y equals mx plus b. What's the slope? What's the y-intercept? The y-intercept is 0 and the slope is 1. So we're going to go through the point, the origin, because that's our y-intercept, and then the slope's 1, so we rise 1 and run 1. And we rise 2 and run 2. And so this one's going to go through all these points right in there like that. And I could go back the other way with it. So this is a parent linear function, and if you don't know how to graph that one, shame on you. Shame, shame. I know your name. Everybody in the world should know how to graph that. You should be able to graph all the parent functions that I'm going to share with you today at any time in the future. At any time starting on Monday, I should be able to say, okay, half sheet of paper, Or here's a piece of graph paper. Graph this parent function, and you should be able to graph it now. And I think we probably feel okay about this one, right? Cool. All right. So example one, graph a vertical compression of the parent linear function by a factor of 1/5. We're going to graph a vertical compression of the parent linear function by a factor of 1/5. And compare it to the parent function. I abbreviate function with an FN dot, so I'll use that abbreviation more in the future. So we're going to go ahead and graph a vertical compression by a factor of 1/5, and we're going to compare that to the parent linear function. So x, if I think about my parent function, f of x, know what that's going to be. And if I think about my compression, so what am I going to be multiplying all these f of x values by here? If it's by a factor of 1/5, I'm going to multiply everything by 1/5, sure. So it's going to be 1/5 f of x. Okay. So we know the parent function goes through the origin. We know the parent function goes through 1, 1. We know the parent function goes through 5, 5. We know the parent function goes through 10, 10. So what about this compression of it? What is 0 times 1/5 going to be? 0 still. What's 1 times 1/5 going to be? I heard 0.5, not 0.5. 1 times a fifth is the same as 2/10. So it's about 0.2 if you wanted to decimal. But what's wrong with fractions? Could we just say 1/5? Okay. What's 1/5 of 5? 1/5 of 5 is 1. So this is probably going to be a nicer point to plot here. So 1/5 of 5 is 1. And what's 1/5 of 10? 2. 1/5 of 5 is 1, and 1/5 of 10 is 2. 1/5 of 10 is 2. So do we get the idea what's going to happen here? We really only needed 1 point, but I think we got enough, so I'll go ahead and plot these lines. So our parent function is going to look like that. And our other function is going to look like that. There it is. So am I done with this exercise yet? With this example? The directions said graph. I see somebody shaking their head. No, you're absolutely right. We're not done. Because the directions said graph the compression and compare it. Compare doesn't mean just graph it. Compare means, okay, look at them and say something about them. So what could we say about them? They intersect. They both pass through the origin. They intersect at the origin. But how does the green one compare to the red one? Yeah. The slope is not, it has a smaller slope. There's a T word that I'm thinking of, and I know the taller and not as tall doesn't really make much sense, but isn't the red one kind of taller if you're to the right of the origin, or higher maybe? Got to be careful using that word. You never know how some people are going to take that. So anyway, are there any questions, comments, concerns, short debates about this first example? Do we get the hang of compressions and stretches, I think? Cool. Cool beans. Well, this next function that I want to show you, I'm going to show you another parent function. I'm going to show you another parent function. It's y equals f of x, which equals rad x. And this is the parent square root function. This is the parent square root function. Now, normally we don't look at this function until we get to chapter 6. So you're not going to see this again until the springtime. But I'm going to show you this function today because it's very useful whenever we explore these transformations, whenever we explore these families of functions. Okay. So the square root function. You ready for this one? All right. So my table of values, x, and the square root of x. Because remember, my y values come from what the function's defined as, and it's the square root of x. You with me? So in my table, I could have wrote x and y, but keep in mind, y and the square root of x are synonymous. Okay, you with me? All right. So let's go ahead and see what happens when you take the square root of 0. What do you get? 0. So this function goes through the origin. What happens when you take the square root of 1? What do you get? 1. So this function goes through 1, 1. Dude, it's just like the other function so far, isn't it? Now, most people on planet Earth don't know when you take the square root of 2 what you get. It's irrational. Anybody know the decimal equivalent? I don't expect you to. It's 1.414 and so on. Okay, it's approximately 1.414. Okay, so somewhere right about there. Now the next x value that makes sense to choose, I guess, would be 4, right? Because we know the square root of 4 is 2, and 9. The square root of 9 would be 3. Cool. So we got 4, 2, 9, 3. Now, we better try, and notice I say try, to see what happens if we go the other way with this. What happens if we try to take the square root of negative 1? Let's see what the calculator says. Hopefully it wants to work with this. If we try to take the square root of negative 1, let me zoom in on this so everybody can see. If we try to take the square root of negative 1, the calculator says that's not real. Whenever we graph anything in the Cartesian plane, we can only graph things that are real. So this is not real. So is anything going to show up? Is anything going to show up to the left of the origin? No, nothing's going to show up. So this function is the first time that we've seen evidence where there's not going to be an arrowhead necessarily on the other end. There is an arrowhead there, but if we were to zoom in here, let me get my magic marker here. If we were to zoom in right there at the origin, that is where that function begins its life. That is where that function begins. Okay, it was supposed to zoom in. In my magic, there it is. That's where the function begins. It doesn't go anywhere to the left of that. Okay. Any questions so far about this function? All right. So what I'd like to do is I'd like to take a minute and explore what happens if we graph. Example 2, let's try to graph the parent square root function, the parent square root function, and f of x equals the square root of x plus 3, like that. And compare them, Okay, so I'm going to go ahead and kind of make this big. I'll send it to the back, lock it in place. Okay, so we could graph the parent square root function. It's going to go through the origin, 1, 1, 4, 2, 9, 3, Woo! There it is. There it is. So here's my table. X, f of x, 0, 0, 1, 1, 4, 2, 9, 3. Okay. So this other one is this f of x. I bet we could. Well, if we plugged a 0 in there, if we plugged a 0 in there, we'd have the square root of 3, wouldn't we? And the square root of 3 is approximately 1.73. Now, if we plugged in a 1, we'd have the square root of 4, which is 2. Okay. So this one's going to go through the point 1, 2. 0 is going to be 1.73. Now, can anybody interpolate, or can anybody realize that this point here and this point here are kind of the same relative point? Does that make sense? Okay. So based on that, see if I can get a highlighter going. From here, relative to that point, we kind of went over 1, 2, 3, and down 1, right? So if I start here, I could go 1, 2, 3 over and down 1. Okay? So if I'm plotting this other point, if I plugged in a -2, the square root of -2 plus 3 would be the square root of 1, which is 1. So the blue function is going to go through the point -2, 1. Does everybody see what I got going on there? I know this is kind of confusing. Okay. And similarly, so see if I can get my highlighter back. Okay. So if I just went one more over, I guess I would be down here on the x-axis. And so the blue one's going to kind of look like that, isn't it? So how does the blue one compare to the green one? How do they compare? Are they the same height? Are they the same? Let's see. Oh, it's supposed to go through there. Let's try to sketch that again. Are they the same height? Are they the same shape? Same size? How do they compare? What's the deal with the blue one? It's a translation of which way? To the left. How many units? 3 units. So if we look at this right here, that tells us this thing translated 3 units to the left. Otherwise, it's the same function. Interesting. So here's the second type of transformation. The second type of transformation for f of x, for any function f of x, f of x, comma, f of x plus k is a horizontal translation. Notice where I put the k. I put the k inside parentheses. Now, if we look back at that last function, do you see how my parentheses is actually a square root? Does that make sense? Maybe it does, maybe it doesn't. So for any function f of x plus k in parentheses is a horizontal translation. So in other words, if we wanted to translate something horizontally, we have to add something to the x. What if we wanted to translate something up or down? How do you think that's going to be different if we wanted to vertically translate something? add something to the y. Great observation. So if we wanted a vertical translation, if we wanted a vertical translation, what's that going to look like? It's going to look like f of x, what? Plus this constant k. F of x, remember, is synonymous with y. Remember when I said that earlier? Now there's kind of a subtle difference here. So if we add a constant to the end of the function, that's going to translate the thing vertically. So this is the second type of transformation. These are called translations. Translations are when you take a function and just move it from one location to the next. It's the same relative size, it's the same relative shape, it's just quote unquote moved. It's located in a different place. Okay. Real quick, I'd just like to go to the graph on the Inspire just to kind of show you a few of these. Insert listen spreadsheets. No, insert graphs. Here we go. So if I graphed the square root of x, we can see what that looks like. Now the next one we just graphed was the square root of, it was x plus 3, right? X plus 3. And we saw that that one's translated to the left. So what if we had something like the square root of x and then minus 7? Actually, let me make that minus 4. What's that going to look like? It's going to be a vertical translation, so it'll be just like the blue one, but moved down 4 units. All right? So far, so good? Making sense? Any questions? Am I losing you? Okay. Well, there's another kind of function that we need to see. The third parent function, another parent function, y equals f of x equals x squared. We'll be studying this in about a week's time, well, about 2 weeks' time. This is the parent quadratic. This is the parent quadratic. This is the parent quadratic function. Okay, this parent quadratic function goes through, well, f of x is actually x squared. So this goes through the origin, it goes through 1, 1. Dude, does everything go through the origin of 1, 1? It kind of seems like it, doesn't it? But they all don't. Oh, what happens when you square 2? You get 4. So this one goes through 2, 4. What happens when you square 3? You get 9. And if you square negative 1, you get 1. Wait a minute, is this thing going to be symmetrical? Yes, it is. Negative 2, 4, and negative 3, 9. So this is the parent quadratic function. I'm sure that you probably saw that in Algebra 1. Probably saw that one in Algebra 1. So we're going to look at one more parent function, and then we got to see the last type of transformation, and then I guess that'll be it for the day. Ready? So the last parent function, I said we'd see at least 3. We're seeing 4. The last parent function of the day is y equals f of x. Well, y equals f of x equals that. This is the absolute value function. This is the absolute value function. And so next week, the first lesson of the week, next week, we're going to be taking these and we're going to be graphing these without graphing calculators. I expect you to be able to graph these and apply all the stuff from this lesson and graph these and translate them and stretch them and do other things with them. Okay? So x, absolute value of x, 0, 0, 1, 1. Wow, everything we've seen today goes through 0, 0, and 1, 1. Oh my gosh. Negative 1, 1. Whoa, this is kind of like the squared one. Well, not really. 2, 2, negative 2, 2. So the difference between this one and the other one is that this one has a couple of rays that go like that, whereas the squared function is more U-shaped, right? So those four parent functions that I showed you, the square root function, the absolute value, the quadratic, and the linear, you should be able to graph all four of those at any given time from now through the end of the year. I expect that you know those inside and out, forward and back. Just to see if we kind of get it, suppose this green function is the same size and shape as that red one, but I go ahead and move it over here so that its lowest point is at the point negative 4 comma negative 2. Does anybody think that they could give me the equation of that? What do you got? Y equals f of x, which equals, so we're going to have some kind of absolute value, right? We're going to have an x in there, and then what? There's going to be a 4 where? Inside the absolute value or after it? Inside, and is it going to be plus 4 or minus 4? Yes, awesome, yes. X plus 4, and then what? And then minus 2, heck yeah, nice job, good, yeah. Yeah, if you don't get that yet, don't sweat it. We're going to talk more about that next week, okay? Awesome, good, really good, I'm impressed. Cool beans. All right, last thing of the day. Here we go. The third type of transformation for f of x, for any function f of x, for any function f of x, negative f of x is a reflection about the x-axis. Negative f of x is a reflection about the x-axis. How do you make something where all the y's are negative? Just put a negative sign out front, and it's going to make all the y's negative. That's going to reflect the thing across the x-axis. What if you wanted to reflect something? About the y-axis? What would you have to do if you wanted to reflect something across the y-axis? To reflect it across the x-axis, you got to make all the y's negative, right? So to reflect it across the y-axis, you got to make all the x's negative. So what's that going to look like? Yeah. F of negative x. Nice. F of negative x. F of negative x. Good. So this third type of transformation then is a reflection. Reflections can occur across either the x or the y-axis and other lines for that matter, but we're going to be more concerned with reflecting things across the x-axis. Okay? So we just got one more thing, and then that's it. I know it's been a long lesson. I know we had a lot here. I'd like to give a shout out to the future Mr. Minnick. He's probably in the back taking copious notes, watching to see if anybody's on their cell phones, hoping that they're not. Would anybody like to give a shout out to anybody? No shout outs? No shout outs. I'd like to give a shout out to my 2nd and 6th period classes. Okay, so let's see if anybody can come up with the equation of this. So that's the square root function, isn't it? That's the square root function. So we'd have y equals, well, I guess I'll make it red. Y equals f of x. Y equals f of x, which equals some kind of square root. Now, if you picture the parent square root function, the parent square root function looks looks something like this, right? Now, did we reflect that across the x-axis or the y-axis? Across the y-axis. So underneath the square root, when we have our x, that's going to have to be what? A negative before that, isn't it? And then since the thing was translated 5 units to the right, it would be x what? Minus 5. And then since it's translated 8 units up, plus 8 on the end, right? Let's quickly see how we did. Square root negative x minus 5, the quantity, plus 8. I hope we got it. I hope we got it. Tab, square root, parenthesis, negative, parenthesis, x minus 5, plus 8, plus 8. And I got to zoom out. Menu, zoom, out from here. I think we got it. That's it, isn't it? Nice job today. I hope everybody had a good day. Monday. Would it be fair to give a one-question quiz on Monday? Be ready. Be ready. Have a great day. See you next time. Good.